In this video we're going to have a look at how a charge capacitor will discharge through a resistor. Initially what we're going to do is we're going to consider the amount of charge on the capacitor and how that varies with time, and then we're going to build it up so we can have a look at how the potential difference changes with time, and also how the current flowing through the circuit is also changing with time. Initially we're just going to have a look at it sort of qualitatively and get a feel for how it goes, and then in the second half of the video we're going to have a look at it in a more mathematical sense, and we'll derive it using calculus. Here we go then. On this capacitor we've got 8 charges that I've drawn on, and so to begin with, what's going to happen, we've got a large potential difference because potential difference is the charge divided by the capacitance. So the first amounts of charge are going to be able to zap around nice and easily, but as we decrease the amount of charge on here, these ones, well, they're being repelled less by them, and now they're being attracted less over on this side because we're cancelling the charges out. So over on the graph here, if I just select myself a better pen, let's go with white. Initially we've got a charge of Q0, and then in a certain amount of time what we'll have done is we will have halved the amount of charge on the capacitor, so we've got Q0 over 2, and that's happened in time t1/2. Now as we continue to discharge our capacitor through the resistor, now every bit of charge we take off is going to be going at a slower rate compared to the previous one. And now when we had 4 on there, and now we've gone down to 2, we've halved the amount of charge again, and what we should find, not very well drawn, it's meant to be a nice smooth curve, but what we should find is the next period of time is again another t1/2, and hopefully you're getting the idea with this. The time it takes to halve it again, so for the time it takes for 2 to go down to 1 will also take the same amount of time again. And even though I haven't drawn it here because I can't split this one up, but if we will halve again, and it keeps doing this and in increments of t1/2. So when we have a process that exhibits a constant change in proportion in equal units of time, we say that there is an exponential relationship. So here the time it takes to halve is the same as when it halves again, which is the same as when it halves again, which is the same as when it halves again. So we can say that the rate of decay of the charge is exponential. So here we are. If we look at the charge again, as it comes down we get this exponential decay where it's always trying to get closer and closer to the no charge left on it, but it can never quite get there, well, only after an infinite amount of time. So we say that it asymptotes on the Q equals 0 line. Now if we look at this, if this is how the charge is doing it, and we want to see what the V is going to be doing, well, we already know the relationship because we know that Q is equal to CV. So if we rearrange this, let's just get a better colour, we can see that the V is equal to Q over C, and because we're not changing the capacitance of our capacitor, we're going to get the same kind of relationship with V. So V will also decay exponentially and asymptoting out. Now when we consider the current, what we need to think about is, well, we know that the current is the rate dq of change of charge with time, so dq by dt, and what that means is at any particular time, if I have a look at what's the gradient of this line, I can see that the gradient is getting smaller and smaller and smaller, and the gradient is the change in charge divided by the time. So again, over here, let's choose a better colour. Let's have a nice orange one. We also have the same relationship and the same shape graph, and all three of these will decay and they will halve in proportion with the same time for each individual one. Right, now we're just going to consider this circuit here. So when we've got a switch over in this position, the capacitor is going to gain a charge of Q0, so that the potential difference across the capacitor, V0, is going to equal the EMF of the battery. Now, when the switch is moved over to this position, the discharge process begins. Suppose that at a time t, the charge has fallen to Q, and the PD is V, and there is a current flowing. And the current will be flowing in that direction. So what we can say is, at this moment, the size of that current is going to equal V over R. And this is going to be equation 1. We can see that when the switch is like this, we're going to charge up the capacitor and we are going to put on it a charge of Q0, and there will be a potential difference over the capacitor of V0. Now, when we move the switch into this position, then the charge, the positive charge here, the current is going to flow around this circuit and start to come to that point. So, if we consider the situation at some time t after the discharge has commenced, then we were going to have a potential difference over the capacitor of V, and we'll have a potential difference over the resistor of VR. Since there is no EMF in the circuit, and therefore by Kirchhoff's second rule, we can see that V plus VR must equal 0. And such that we can build on that and we can say that nothing equals, well, the potential difference over the capacitor is going to be Q over C, and the potential difference running through, sorry, the potential difference over the resistor when there is a current I flowing through it is going to be IR. With the switch in this position, the capacitor C is going to gain a charge of Q0, so that the potential difference across the capacitor V0 is going to equal Q0 over C. And this is going to be equal to the EMF of the battery. Now, when we flick the switch over, the capacitor is going, the discharging process is going to begin. And suppose at a time t, the charge has fallen to Q, and the potential difference is V, and there is a current flowing of I in the circuit. And such that the size of the current will equal V over R. In a short time, delta t, a charge equal to delta Q flows from one plate to the other, so that I equals minus delta Q by delta T, and the minus sign is showing that the charge on the capacitor has become smaller. Now, for the capacitor, the potential difference over it, V, is going to be equal to the charge stored on it divided by the capacitance, and if we eliminate I and V, we are going to end up, sorry, just checking my notes there, we're going to end up delta Q is equal to minus Q over the capacitance multiplied by the resistance multiplied by the very short time interval. Now we could rearrange this so that we get delta Q over Q is going to equal minus 1 over CR delta T. Now if we take this to the limit, we can see that we get dq by q equals minus 1 over CR dt. And if we rearrange and integrate between the original charge Q0 and Q with respect to time, we can see that we get that the charge on the capacitor will equal the original charge on the capacitor multiplied by E to the minus T over CR. Now, because we know that V equals Q over C, if I divide both of these Q's by C, or just divide both sides of the equation by C, we can see that we can get a second equation, which is going to be that V is equal to V naught E to the minus T over CR. And finally, if we differentiate this with respect to time, we'll get dq by dt, which equals I, and that will equal I naught E to the minus T over CR. Now we've got these three equations. Even if you didn't understand how we derive these three, it doesn't matter. All we need to be able to do is manipulate them in order to be able to solve problems. Because all three of these equations, for the charge, the potential difference and the current, they're all in the same form, then the following process is you're getting 3 for 1, as it were. So I'm just going to deal with the charge, but you can just substitute the Q's for V's or the V's for I's. It's up to you, depends on the problem we're trying to solve. So if we do this, we've got it written in the exponent form, so let's just write it out again a bit bigger. Q naught E to the minus the time over the capacitance times the resistance. Now in a moment we're going to have a look at what the capacitance times the resistance is and its significance, but at the moment I'm just going to write this, but instead of writing it in the exponent form, I'm going to write it in the logarithmic form. And because we're using the base E, we're going to use the natural logarithm. So, in fact, just before we take the logarithms, I'm just going to rearrange this, and that's going to say that Q over Q naught, so basically the ratio of how much charge we've got left compared to what we started with, is going to equal E to the minus T over CR. And if I just go into a different colour, because we're just going to do a little maths trick, if you've got x to the minus 1, then that is the same as 1 over x. So if I didn't have the minus sign here, then we're going to flip this equation up over here. So that's going to give me Q naught over Q is going to equal E to the T over CR. Right, now we're going to take logarithms. So if we take the natural logarithm of Q naught over Q, and that's going to equal the natural logarithm of E to the T over CR. So if I just extend the page, and let's go back up. Right, from the rules of logarithms, if we've got an exponent here, then that's the same as just writing out the log, but multiplying it by that exponent. So that gives me T over CR, natural logarithm of E, and again, using the rules of logarithms, well, this is base E, so what this part here is now actually asking is, what number do I need to multiply E by in order to get E, and of course the answer to that is 1. And again, if we look at our rules of logarithms, the quotient rule, then if we've got a division inside this, then that's the same as just subtracting the two individual logarithms. Q equals T over CR. Right. Now, if I rearrange this, I can get myself to the following situation where I've got natural logarithm of Q0 minus T over CR equals the natural logarithm of the charge that is left on the capacitor, or I'm just going to rewrite it out into a slightly different way. Natural logarithm of Q equals minus T over CR plus the natural logarithm of the original amount of charge. Now, the reason I've written it around like this is because some of you may have already spotted that this is in the form of y equals mx plus c. So, if I had a graph and I was to plot the natural logarithm of q, there's my white. Natural logarithm of q on the y-axis and t along the x-axis, I should get a straight line graph with a negative gradient coming down something like that, where the intercept of the line is going to equal natural logarithm of Q0, and a gradient of minus 1 over CR. Okay, so now in the next part we just want to have a look at what's the significance of CR, which is the capacitance multiplied by the resistance. Now, it can be shown that the SI unit of CR is equal to the second. It's quite tedious to do it, so I'm not going to bother doing it in here. If you do want to have a play with it, or if you're unsure how to do it and you're really desperate to see it, come and find me and I'll show you how to do it. Right, it's given the name of the time constant because it's obviously equal to the second, and just want to have a look to see what would happen if we discharge a capacitor through a resistor for a time of the time constant. So let's have a look at that. So the amount of charge we're going to have is Q0 e to the minus t over CR. However, if we're going to discharge for the amount of time that's equal to the time constant, then this whole term here becomes minus 1. So that gives us Q equals Q0 e to the minus 1, and that can be written as Q equals Q0 over E. So in a time of the time constant, what we can see from this is that the amount of charge that's left is going to equal 0.368 Q0, which is approximately equal to 37% of the initial charge.